שלום לכולם. אנחנו עוברים עכשיו להצעת התלמידים. We're moving on to a more provocative lecture by, I think, the first student. True? You didn't retire.
I was flattered this morning by Tom Dan, who mentioned Ya'ir and line 73. I am the line from the 73, but I betrayed this topic. I'm not dealing with the last 25 years. I am not in the field of geomorphology. I am more in the field of coastal geomorphology. And being a coastal geomorphologist, I came across the question of sea level rise, yes or no. And I am not coming to attack the problem from the point of view of a climatologist. So you want here CO2 and greenhouse, and I'm not coming from the point of view of deep ocean, oceanography. And therefore, they won't be hot current or cold current. I was just involved in many studies which were looking on changes in the Israeli coast along the last 100 years. And before I start my presentation, I go into our Jewish sources, because we have to deal with cycles, and we understand whether or not we have cycles in nature. And the Babylonian Talmud tells us that when the first Adam was born or created, never mind what was the process, that was around the 21st day of September. And Adam Arishon did his sin, and since then he realized that the day is getting shorter and shorter. But luckily enough, the moon also changed its shape. And he said, well, maybe there is a cycle in nature. And he was right. After a month, the moon was reborn. And he waited another month, and yes, there is a cycle in the moon. But the days are getting shorter and shorter, and he said, well, that's because of me. That's my sin, and the world is going to collapse because of that. Luckily enough, 31st of December arrived, and suddenly the day increases. And we realize there is another cycle on top of the first one. And why I am telling that? Because in 1972, the year that I finished my master's with Aaron, a very important geologist, I met him later by the name of Kukla. He was a Czech by origin, but he lived in the United States. And he and his fellow mate Matthews, they wrote a letter to the President of the United States, that was Nixon at the time, saying that we are going toward an ice age, and that was in the time of the Cold War. Beware, the Russians already into research. And they didn't send the letter only to the President, they published it in a paper, 1972, we are approaching the end of the interglacial. That was the idea in the science at those days, and Nature published a paper where there is a consensus over all all the scientists that the world is going toward an ice age. Nowadays, when I am living my academic life, the idea changed completely. And I'm asking a small question. There is an accumulation of 6,000 years of information, and we are still doing conclusions the same way that primitive Adam did his conclusion. Just think about that. And the IPCC is an intergovernmental panel for climatic change, which is one of the leading institutes in the world. They also changed their mind within the last 25 years. In 1990, they wrote, no evidence for sea level rise. 10 years later, yes, there are evidence, sorry, but that is in less than a millimeter a year. And nowadays they are claiming at least 3.2 millimeters a year. So within short span of time, they are changing their idea. And then obviously there is wow, the moon picture. Are we going crazy? That is a map published by the United Nations in 2005, claiming that by the year 2010, we will have 50 million climate refugees. Where from? From Delta's area, those are all the black points, then lowland sea level area, and then desert and permafrost. But what happened? 2010 passed, and there was no 50 million. So they repeat the claim, and the claim say in 2011, the 50,000 are still on the news, but it will be by 2020. We are now in 2017. I can't see the number of the climate refugees. And we have to remember at the time we said that Kukla wrote that the same way of frightening the people was in the world. And you see just that small samples of many, many papers, they are all claiming that we are going toward an ice age. Some numbers, because most of you are not dealing with ocean processes. If we change the pressure over the ocean, a deep ocean, 4 kilometers, by 1 hectopascal, which is fair enough, 1 millibar, we change the surface by 1 centimeter, just because of the pressure. So the sea level is breathing all the time because that's nothing. And then that's the other one, to change all the column of water by 1 degree, because we have the thermocline and so on. That's more theoretically. But if we change a 4 kilometer depth of ocean by 1 degree Celsius, the ocean will breathe by 60 centimeters. Opposite way will be in the case of more salt in the water. I won't go into it. And the last factor that I want to tell you is that if we met all the ice in the world, meaning Greenland and Antarctica, the sea level will rise by about 70 meters. And if there is any climatologist here and tell me, well, I read 80 meters, I won't argue with it. I buy 80 meters as well. And those are actual values that you have to take into your research. For example, we wrote a paper on the Mediterranean Sea, and we took the 4 longest record stations in the Mediterranean Sea, Trieste, Venezia, Genova, and Marseille, and we see that during the years 61, 62, and 85, 86, sea level wasn't changing much. You see a straight line here in all the stations. And then we went into the climate people, and we realized that during that period, the average pressure on the eastern, mainly the eastern part of the Mediterranean, was higher, and therefore the water level was lower. And if I'm going to the big place, Antarctica is melting, and every one of us sees the TV and it sees the breakdown of Antarctica. But what can I do? 18 months ago, NASA published their own research and claiming that Antarctica is gaining ice, 82 gigaton a year. That's by NASA, not by Michael. Yes, that is the area where you have breakdown from Antarctica. And it's very nice to take a photograph there, because it's nice to take a photograph here and to say, well, the height of the ice is 3 centimeters more. It doesn't make any impression, but those are data by NASA. And the other one, there is a scientist from the Hebrew University in Jerusalem, in the physics department, by the name of Yאיר. He is claiming that argument for the last 15, 20 years, that sea level is basically connected to sunspot. So I went into it because that's his field. But I just took the 400 years, the last 400 years of sunspot activity, and we started counting them in 70-50. And each cycle is 11 years, so we are now in the cycle 24 or 25. And you see that over the time you have the 11-year cycles, but you also have on top of the cycle another one, which created cold area. And here are the 20 years that Kukla felt, and that's the reason he wrote the letter. But he also didn't realize that this may end. And now that's a nice one, because that's exactly the same graph, but it tries to predict the coming 30, 40 years. And in the year, on 5 to May 45, 2045, I will be exactly 100. And there will be an argument industry that the climate dropped by 0.6 degrees. And all the activists who want to burn the fuel say, well, we are lucky that we burn the fuel, because otherwise it would have been down by 0.9 degrees. And that is the way we are acting in science. And then I went into a new problem which I never came across before. And I think that 80% of the people who here who deal with geology never thought about it. Because on the globe we have 3 different surfaces. One is a topography surface, which we all know because that is familiar to us. The other one, which is mainly familiar to the geodesists, and that's the geoid surface, which is not smooth but has some sinuosity. And the third one is the ellipsoid. And what is the ellipsoid? All the time that we measure height from ground, we put the name and so on. But the minute we went out to space, and we are measuring height back to surface, so what are we measuring? Here is the satellite, launching some 100 kilometers above the surface. If the 100 kilometers is to the high point here, or the 100 kilometers is to the low point here. And there is a difference. And obviously we get many funny results because we are not familiar with it. The biggest company in the world to produce data on GPS, RSA, they are located in California. And they checked the map of the headquarters, and it was 400 meters above sea level. And then they repeated all from satellite measurement, and it was 32 meters lowered. And obviously that's a very well-known one, that the globe itself is dynamic and it changes every year by the same amount that we are claiming that sea level is rising. And therefore you see, and I brought this out of many, many others like that, because here you see, you see this pink area, pink color here. We all know that the eastern side of the United States is many, many floods are coming on the surface. But what can we do? That is the area which is subsidizing by 10 millimeters a year. So maybe all the flooding is not because sea level rise, it's because of subsidence of the area. That's the only one graph that I wrote concerning temperature. Because I decided temperature is not the topic today. Global warming is the business of different people. And that's just to show you how sensitive are the data of changing temperature. The right graph is the same area, two very distant companies in the United States. One is NOAA and the other one is the Met Office of the United States. And they are referring to the same period, and all the data of NOAA is higher than the data of the Met Office. And the other one, when you measure temperature on the Earth's surface or by satellite, here is the same period, one by NASA taking measurements on landscape, and the other one is satellite data. And the satellite data show us no increase in temperature over that period. So when you read a paper, did you ever want to see whether or not it's satellite measurement or surface measurement? And that is the prediction versus observation. That's what the IPCC reckoned after taking 1900 to 2000 as the calibration period, and that should have been the rise in temperature, and that's what we actually measured, and that's the same idea from a different source, and that's one of my gurus on this topic, Murner, and he is one of the very, very strong fighters against the climatic warming problem, and he did the same trick there. And now I'm going to the source of data for the rising mean sea level. And there are three sources of data. One is the Permanent Service for Mean Sea Level, which is an institute located in Britannia, and has all the data from time ages all over the world. And the other one is obviously satellite data, and the third one is which geomorphologists we like them the best, and that is field evidence. And this guy wrote a paper of an old picture in Tasmania showing the mark of sea level in 1841. And he went back after 158 years, and the mark was exactly the same. You see the line with the arrow, the line with the arrow. So field evidence shows us no sea level rise. But to be honest, if I take the Israeli coast, and that's the well indoor, and you see that in 1915, a German visitor in Palestine, said, well, I saw people taking water out of that, and nowadays, obviously, no way. So there is a rise of 20, 30 centimeters for sure. And that is one of the worst graphs I ever saw in my life. Because, first of all, anyone who read the graph say, well, we have an increase in water level of nearly 3 millimeters a year. Good. But the first point, if you take the same company a few months later, and you suddenly realize that they increase the value by 15%. Why is that so? because here it's with no correction, and here it's with correction. And I won't go in now to the short time what is the correction. But the more important thing about this graph is that all the 7 satellites they are using, they give the same result. When my first year tutor in physics lab got the same result from the group, he gave 0 to all the groups because they were quoting each other. And you can't believe that all the different satellites will give the same result. And therefore, I went in and checked them. Those are the 3 first ones, topic JSON1 and JSON2. The actual data of them wasn't, they were not matching. The data was, the trend was okay, but the data was different. So they smoothed the data and came out with this graph. And then the European sent another satellite, which called NBSat. And the data of the NBSat, once again, didn't fit the findings of the first one. So what they did, they corrected the data and came out with this graph. And we all live happy ever after, because in a minute. In a minute. Okay. And they launch another one, and that is Grace. And once again, the data from Grace are here, and they corrected the data, and that's it. So I don't know if one can believe in the data of and then I come to the third and the last source of data, and that's the permanent survey from WITS 11. And those are the project of GLOS station all over the world. But here, once again, I face a problem. That's develop because all the old stations are all located on Europe and on America, which are by definition increasing in height because of the rebound. And therefore, if I take the permanent service for wind and average height, is that some? But here is a problem, because if you take station by station, you see very different patterns in different stations. And Tom, we speak English because of your honor, so remember, there is 1 meter. There is 1 meter increase in Bangkok. You remember that? Because if I go and I jump, you see, I jumped it all. I came to this table, which is just measuring subsidies of urban area along the coast. And I go back to Bangkok. That's the reason I asked Tom to remember the 1 meter. And what is the subsidence rate in Bangkok? 1 meter. So what's going on in Bangkok? I don't know. Yes, number of floods increase, that's definitely true. But the number of floods may increase either because of sea level rise or because of land subsidence. And obviously land subsidence is order of magnitude more than, and that's the last one. So again, that is the place with the highest subsidence in the United States. And I don't know this guy, but I believe in my science. So from 1925 to 1977, 50 years time span, there is at least 10 meter subsidence of the land. And if that's happened in the coast area, obviously we are in a problem. Those are the conclusions I went over them. I just mentioned these 2 guys, Australian. Fantastic work they did. They took all the rain station of the world and they came out with a very important conclusion. The satellite altimetry is just unrealistic for the measurement of sea level change. Yeah, it's useless for that. And that's enough. Thank you very much. It wasn't what
Okay. Question to him. Later. Okay, the next talk. Okay, Camille Brother. The influence of floods on life and ecology of the people, oasis media. חיים יוצא בזמן.
Okay, when Aaron went for his retirement about 7 years ago, I think 7 years ago, something like that, 85 minus, it's about 7 years ago, yes.
17 years.
Wow. Anyway, he gave me two items just when he went for his retirement. One is his personal measuring tape that probably he carried with him for tens of years in the desert, in the fog, in the dust, in very hard work. And I joined Aaron for several field expedition drilling, and I know what's the meaning. And the second item is the whiskey flask. And really, he gave me these both items.
Empty or food?
No, it was half full, yes. And I think that both the men.
Do you still have it? It's in his pocket.
Yes, of course.
It's just the cane. Both
Both of them.
Give it back.
And I think that maybe both of them may represent our own entire academic life. I don't know which one influenced more his life, the measuring tape or the whiskey flask, but let's say both of them together gave excellent results. And thank you very much, Aaron, for the excellent evening and very good food after the hard days work in the field.
What about the suits in the field?
Okay, my talk, jump one. Okay, I will concentrate in my talk. We see here the map of Africa, the entire map of Africa, and even from here, to see the entire map, we can see here a distinct area with some gray area and a sharp contact with some white area. And if we enlarge a little bit the map, we see this sharp contact in this frame of the map. And if we are going closer to look at this side, we see the Namib Sea advance to the north in a rate of few meters a year, and somehow the Sea didn't go over to this linear oasis, the Quisel River, didn't go to the north of the Quisel River. And this Sea, the Namib Sea, is about 300 kilometers long. It started just at the border with the Orange River, that probably originates some of the materials, but here this border we were curious about how it works and what's the dynamic along this lifeline in the extremely arid desert in Namibia. And we can see that the rainfall dropped from about over 350 millimeters on the higher and upper areas and go down to about 10 millimeters, some years 0 millimeter, close to the coast because of the cold Venezuela current. And usually the flash floods originate only on the upper section. The flash floods cross for hundreds of kilometers through the Great Escarpment, through the Namib Desert without any additional water that's coming to the system. And if we are going to the river, we see the very sharp contact between the 300 kilometers of the Namib Desert and the riverbed. We see here another photo, the very, very sharp border, and we see that the Namib, the Quiseb River influenced very much all of the environment before the northern part and the southern part of the river. And just evidence that Yehuda was there, and we see the dunes coming every year in a rate of half a meter, 1 meter, 2 meters, 3 meters. They start to invade the stream, and the stream have enough force, enough floods to carry the sediment out of the river. And if we are looking for very, very long term, that's somehow an evidence of the climate of the area, that if we are assumed that the climate was a little bit with less floods, we probably find some dunes that then cross the river. Because if we are talking about a rate of a few meters a year, and the width of the valley is about 200 meters, it's quite easy for the dunes to carry on and to continue. So what we can learn from this image? First, the flood frequency, it's enough to take all the invaded sand, to distribute the sand along the valley itself and on the floodplains. Second, the linear oasis that we see along about 100 kilometers in the desert, that's, let's say, the only lifeline for hundreds of square kilometers, is based on the material that came from the sand, from the Namib Sand Sea that deposited in the stream itself and create excellent aquifer for storing the flash floods. We have to remember that flash floods that originated on the higher and wetter area, they travel for hundreds of kilometers, and the flash floods are for very short period, for days or sometimes weeks, and later the aquifer need to support the lifeline for months and sometimes in a drought period for years. So the aquifer functions very well in this condition. And if we keep going and looking at inside the Quiseb itself, and we look at the trees, we can see differentiation in trees type. In the one part, the closed part of the active channel, it's one type of tree, the anaphum, that enjoys the fresh water. The second is the acacia or camel thorn that stay on upper terrace and in more drier and can stand more drier condition. And it's the last, the tamarind, just at the edge of the floodplain with a little bit more salty water. So just from this image, we can start to feel what's happened to this system, what's going on with the system, with the groundwater, because there is the only source for the tall trees in this area. From the migration of the sand, we understand for long term the existence of this lifeline and the possibility of transport the sand. And also the last point is the tree condition, that the trees that can maybe tell us something about the aquifer itself. And here is another photo that's much more the story about the different places along the cross section in the river and the different trees and the different conditions that each one present. And if we can say something about the trees, the condition, the health of the trees, maybe this health can give us some prediction, some indication of floods in the area. And we know that in many agricultural areas, we use some satellite images to figure out the condition of the trees. And before I'm entering to this point, if we can look, here is the Guisev, and if we are going south, we see that another stream with smaller catchment, with less rainfall, because as we are going south, less rainfall is presented here on this mountain. So less rainfall, less catchment, the rivers they don't have enough floods to overcome the Namib Sea, and they stop just at different points. And here is just at the beginning of the Sensi, and the beginning of the Sensi, and this river just ended here. So the frequency is probably the flood magnitude and frequency are probably the cause for clearing the sand from advancing northward. I'm going forward. Okay. And here we can see, we look at the trees in the stream. Picture from 2004, 2011. We still see some floods mark in the channel. We see more life in the trees. 2012 still we see more bright color, and then 2016, few years after the flood, 5 years after the flood, it goes back. So the trees could be some indicator for us, maybe for flooding frequencies or long-term flooding frequencies. Another point is that in some places we see dead forests. We see here the active channel, the trees, and then on higher terrace you can find some dead trees. We call them dead forests. And this dead forest, we have like two possibilities to explain. One is that during drought years, the groundwater falling down quite fast, the roots cannot follow the groundwater, and we got a dead forest. And the other possibility that we had extreme flood. The flood was overwhelming the floodplain. New forests start to germinate from seeds, and then it was falling of the aquifer level, and the roots cannot continue to catch the water, and therefore we have the dead trees. Here is some illustration of how the system is work. It's a real measurement. The different kind of trees, the root depths, and the aquifer level in the alluvial cross section. Here is something quite interesting. We see the trees' roots just in a line that is between about half a meter or 1 meter below ground, down to 1.3 meter below ground. If the roots getting deeper, the floods may fill up the aquifer and the roots cannot exist anymore. And if the roots are on the upper place, when the upper section of the active channel, because of scour and fill, they will fail to survive. So there is a very limited, like half a meter or 1 meter of width that in the alluvial part of the valley that the roots can survive. And here we can see very interesting figures about floods and aquifer level. We can see that for long term, the normal flood, the average flood, they cannot support the ground level. The ground level decreases all the years. Only extreme floods increase the groundwater. That's the groundwater, and that's the extreme floods. And just during extreme floods, the groundwater level rises. During normal years, the normals cannot support the water level for long term. And we see that extreme floods rising, another extreme flood, and another extreme flood. So basically, we understand from the fact that the dunes are not advanced to the north, that the extreme floods are control the barrier between the Namib Sea at the south and the gravel plain in the north. And for long term, this kind of extreme flood exists. No other way that the lifeline along the oasis exists, and also that is the barrier between the. I will skip this one maybe. There is some drop here, but I'm short in time now. Okay, and that will be my final graph. We take the NDVI that represent the health of the leaves of the trees, and we can see that with the floods, there is increase in the NDVI index. And during 2009 and 2010 and 11, it was occurred the most extreme flood of the last century in Namibia. For example, at the further north in Windhoek, that's the average rainfall is about 350 millimeter a year. It's get to 1,300 millimeter. We have very large flood, very large volume, and very sharp increase in the NDVI values. So what we are thinking now is maybe to use this as a tool to investigate floods in arid and extreme arid areas and to see how this works. Thank you very much.
And the next talk is by Ente, the geomorphic historian of Nachal Arava to get sea level fall.
Thank you. Yuri, I'm very excited to show you today. Today I present our research on channel evolution in response to continuous base level lowering, and specifically on Nachal Arava channel evolution in the decades that respond to large and rapid level fall of the sea in recent decades. The general questions we are dealing with in our research first is how does the channel evolve in such a situation of response to continuous base level fall? And secondly, what are the factors that are governing this kind of geomorphic evolution? These questions were studied before, previously, mainly in laboratories, in flumes, or in these numerical models, while field scale, exposed field scale active study cases are quite rare. Some of these studies focused on the evolution, the channel evolution in continental shelf environment as a response, for example, to the sea level, global sea level fall during the last glacial maximum. Here, I'll propose, I'd like to convince you that Nachal Arava case of evolution is an interesting modern analog to this kind of evolution in the past. So, our study area is in this area, the southern basin of the Dead Sea. This picture, this image from NASA from the beginning of the 70s, you can see that all this area was back then flooded, and through the years, so through the 80s, it got escaped, dried up completely, and Nachal Arava, like beginning of the last century, was flowing to here, was elongated rapidly and flowing as it's flowing today to the northern basin of the Dead Sea. If you look at the cross-section from A to A prime, from the south to north, you can see the level flow of the Dead Sea, the exposed southern basin, the exposed big strait. You can see these new segments of the long segment of Nahal Araba. This segment nowadays is artificially perennial, as brines are discharged from this proportional evaporation ponds in the Israeli side and the Jordanian side to the channel, and from the channel these brines are flowing to the Dead Sea, back to the Dead Sea, to the northern basin. This discharge, just to know what we're talking about, is the highest discharge nowadays among all other tributaries flowing to the Dead Sea. So we have this new kilometer-long new segment of Nahal Araba. We have this large and fast level-lowering of the Dead Sea. The topographic and bathymetric setting is quite similar, by the scale and the slope. It's similar to a continental margin environment, where this wide shelf and low slope. We have this shelf break and slope. We have some delta that propagates rapidly, as I will show you in a minute, in the mouth of the channel. And there are some variations in histology, in the substrate of the channel, that can affect the evolution of the channel. So overall, we're looking or studying this area, the evolution of this segment of Nahal Araba. So first, I'm going to show this evolution, what we found. Then I'm going to talk about the factors that controlling the evolution of Nahal Araba. And at the end, I'll go back to the general case and try to suggest Nahal Araba as a modern analog to channel evolution in the continental margin. So this is our study area, the northern 15 kilometers, 16 kilometers of Nahal Araba. This is an image from north to south. You can see here the channel. This is the delta, or the salt delta. This salt delta is made of, or consists of mainly halite, fine-grained halite, unconsolidated, and it progressing fast, rapidly to the north into the Dead Sea, as you can see here in these shorelines. South to this salt delta, most of the substrate of the channel consists of lacus fine bed, laminated lacus fine bed, as you can see here, thin lamina of silt and halite. And in this accent, in this green polygon, or here, you can see there is a thick rock salt layer made of consolidated halite here in gray. So this layer, this rock salt layer, had a major effect on the evolution of Nahal Araba, as we'll see in a minute. So we now jump to some evidence for this evolution of Nahal Araba. We go looking on this area right here in the middle of this thick layer. So now we're gonna look on a series of aerial photographs that we managed to get from different sources. This is from 1992. Again, this is the area. North is here. This is the Dead Sea. So this is the channel over here. Back then it was a wide and shallow channel. Here you see a midpoint, small waterfall, vertical midpoint. That downstream to it, you can see this narrow channel, narrow and deep incising channel. So now we go through this area photograph showing the evolution of the channel in this about 1 kilometer segment. So, and then before you can see the migration of the midpoint to this position. 1996, this is two heads. 1997, 2001, you can see here now the channel is developing these meanders over here downstream to the midpoint. This is July 2001, and this is 2002, while all this segment and the segment that is downstream to here or to this midpoint, all the segment is developed, incising, and reacting to the level fall of the Dead Sea. Let's look on the whole series from here to here. We took these images, we digitized them and put them on a spatio-temporal diagram, as you can see here. This is distance, x-axis, in y-axis is time from 1992 to the beginning of 2000, I guess. And you can see here the major role of this knit point, downstream to the knit point. You see a narrow, incising, meandering channel, and upstream to the knit point, all this part, the modifications are moderate or minor, and the channel is relatively stable. This line is connecting or going through the midpoint, this orange line, and in this diagram, this kind of diagram, spatial temporal diagram, the slope of the line is the migration rate here in meters a year. And here, for example, you can see values that more than 200 meters a year, and these rates were higher after. So you will show it in minutes. So let's look on the total evolution of Nachal channel during the years of the old segment, the old 16 kilometers of the channel. So these longitudinal profiles are reconstructed based on LiDAR data and aerial photographs. We have here from 1990 in brown here to 2013 here in blue. And here in this area you can see the midpoint migration we just looked at in aerial photographs. So you see that this migration from the 1990 to 2001 in yellow, and all this migration took place inside this Roxas layer. So part of the midpoint was inside this layer here in gray. After 2001, all the channel and part of all the midpoints were inside below, to a level below this Roxas layer, and the migration rate rose. This is from 2004, and after 2004 till present, all this segment, all this area of the channel is reacting continuously to the level for here of the Dead Sea. This is how the channel looks today, or in 2014, in this area. You see it's deep, incising channel with bands that are nowadays over 18 meters and continue to incise as we speak. Let's look on this data and first way of presentation. We go back to the spatial temporal diagram. So what you have here is the same data as here, traditional presentation, but now it's arranged in different axes or in grid. This is the distance. Y-axis is time from the 80s till present, and the contour lines and the colors represent elevation, or channel bed elevation from the channel. The field triangles, black triangles, are positioned in time and space of the midpoint. Okay, so now you see the first midpoint, you see its migration, relatively slow migration in these years, and then the migration is the values are rate values are higher. You can see here, for example, the mouse progression into the Dead Sea. So this transition is between the land and the Dead Sea, between the color and the gray polygon. So now this is fast or rapid propagation of the channel mouse, and here you can see relatively slow one. You can see it? It's pretty clear. Okay. So just to make it to emphasize the main processes, you can use this schematic diagram. It's based on this data. So you see here these lines connecting the migration or retreat of the midpoint. You can see that upstream to it was slightly inside, and downstream to the midpoint, the channel inside rapidly. We looked on other parameters of the channel through the years. The same presentation, the 2D plots, the diagram, spatial temporal diagram, and the schematic version of it. This is from the width, and you see again the role of the midpoint wide upstream and narrow downstream. Sinuosity developed only downstream to the midpoint migration, then in more upstream parts. Slope goes higher where the channel is incising, and for this incision rate, the values in the area incision were very high, the values were very high more than half a meter, and in some places more than 1 meter area of incision length. This is a summarizing comprehensive diagram that will summarize all these processes and characteristics of the channel along the years. So again, it's spatial temporal version. And we look what were the what are the factors to control this kind of evolution. We looked on the level change, some major flash flood, but at the end, we go straight to it. We find that the main or the most effective ones were the mouse load that we calculated along the years, and the effective physiology. This diagram just what the values here are saying that the positive values are represent years in which the midpoint was inside the rock salt layer, and negative ones are represent years in which all the channel and the midpoints were inside to a level below this rock salt layer. So let's go through this evolution. So at first there was this lengthening phase or stage as the channel elongated on top of this shelf, and when it reached the shelf edge, the rapid propagation of the delta moderated the mouse slopes, and this stage of lengthening was extended. The second stage started only after the mouse slopes right here rose and reached levels that are higher than the slopes that characterizing the channel itself. Okay, and then we have this second stage with the incision, but all the incision processes, the narrow or the meandering, took place only downstream to the midpoint, as you can see here in this area. This vertical midpoint was maintained by this rock salt layer. Okay, so now control the factor that governs this stage is the solid or the rock salt layer over here. Only when the channel inside below this rock salt layer, we can go to the third stage. Here, when the midpoint migrated rapidly upstream, and then, as I said before, all the segment of these 16 kilometers are since then this segment is reacting, responding continuously to the level fall in the slopes at the mouth. We took these results and we suggest on top and based on that conceptual channel evolution model for channels evolution in the continental shelf. So again, we have a first stage. You can see it here in the 2D diagram and the spatial temporal diagram. This stage of lengthening. If you go back to literature, I think you will not find many studies that are dealing with treating this stage, which can be very long in a case of evolution or response of the channel to level lowering. After the shelf break, or if there is a delta can moderate this, or when the delta start to moderate the mouse slope, the second stage is partially discontinuous evolution, which dominated by this vertical midpoint migration. Here you need this substrate or alternating lithology, which you have hard over soft or resistant over non-resistant substrates, as you can see here. And when the midpoint and the channel are inside below this layer, the third stage will start with all this segment, all the channel will evolve continuously and respond to the level lowering or the slopes in their second base. Of course, this is not, it cannot describe all the cases of channel evolution in continental margin, but we believe that this case of hard over soft or resistant over non-resistant alternating substrate with a rapid propagation of delta can describe some or many cases in this kind of evolution. Thank you.
doing the down cutting and it is doing vertically of the waterfall is the flood, the water. And in your case, most of the water flowing along the barrier are application from the Dead Sea wall. So you have a permanent flow of water in the desert area, which is not natural.
You're right, it's not natural, but we looked at it and we like this case because it's kind of a huge flume, because we have soft sediment, we have perennial or high discharge. You're right, it's not natural, it's artificial, but it gives us this rapid and impressive evolution. Wait a minute. And we looked on flash floods. There are some flash floods, or big flash floods, as you can see here, in this winters or springs, in some of the years. And we found that there are some effects of these flash floods on the morphology of the geographic feature of the channel, but this effect was relevant for in the short time, and not for the short term.
The point is, the real world, those are the main reasons for it.
Maybe for the short
I'll
term.
finish it, but I'll answer one thing. Most of the world is perennial flow. Most of the world. That's the analog.
Okay. Yeah, what?
תעבור.
Hi, John. All is well.